All right, cool. So yeah, like I was saying, um, we're going to be going over the major kinds of chemical reactions, just learn some examples for some, and balancing, just everything to do with equations. So, the first one we're going to go over is the synthesis reaction. It's pretty simple, just two substances react to form one new substance, right? A plus B yields AB. And you can see this, right, with the examples here. Carbon plus oxygen yields carbon dioxide. Um, it's just synthesis, right? They form a more complex layer. And it's the opposite of decomposition, where with synthesis it's A plus B yields AB. With decomposition, it's AB gets broken down to yield A and B. Um, yeah. You can see here some examples, right? Carbon monoxide splitting up in a carbon and oxygen. And note that all of these reactions work with compounds, right? So CaOH2, that still can be broken down into CaO, and H2O. That just still follows the basic form of AB yields A plus B. So another type of reaction that you'll see is the single displacement reaction. It can also be called a single replacement reaction. So in here, basically, you have the structure A plus BC yields AC plus B, right? So basically what you have here is you have a molecule of something and then a lone element, right? And then the element goes and swaps something out from the molecule you have, right? So for example, right, potassium and sodium chloride yields KCl and Na, right? You can see here that the potassium is subbing out for the sodium, right? And now it's KCl and Na. And again, you can see this works with, diatomic molecules, different kind of compounds, all that stuff. Cl2 plus 2 NaBr. You can see the Cl2 still subbing out the bromines. That's the basic structure of single displacement. And next kind of reaction we're going to be looking over is the double displacement reaction, also called double replacement. And it's basically the same idea with a single replacement, right? But instead it's AB plus CB yields AD plus CB. Um, and then here, right, you can see B and D are just switching places, right? So now you have two new compounds coming out of that. And yeah, note that A and C are cations, positive ions that we've learned, and B and D are anions, right? So the anions just flip places, or the cation. And yeah, here's an example. Na2S plus 2HCl yields 2NaCl plus H2S. You can see that pattern AB plus CD yields AC plus BD. And then yeah, most acid-base reactions, right? When we go over those are double replacement reactions. So just keep that in mind. So next kind of reaction is combustion. If I can open it. Okay. So it's a kind of reaction where a fuel and an oxidant, right, usually oxygen, yields an oxidized product, right? So usually, the one that I come across most commonly, right? It's a hydrocarbon plus oxygen yields carbon dioxide and water and heat. So you can see here, a hydrocarbon is just anything with hydrogen and carbon in the name. So one example you come across is methane, CH4, um, and 2O2 yields carbon dioxide and water. And this is the form of reaction that powers factories, all that stuff by just burning. And the last one isn't specifically a kind of reaction, but I still want to go over it. Redox reactions. So redox isn't like a special kind of reaction, but it's a form of reaction, if you know what I mean, that just results in the switching of electrons, right? So you can have like say a double displacement and redox reaction. And basically the definition of redox reaction is that you're yeah, you're swapping out electrons between um different elements, compounds, molecules in your equation. So yeah, you see here, um something really important to remember, right? Redox. One mnemonic that you really want to remember is oil rig. Stands for oxidation is losing and reduction is gaining. Because oxidation of an atom means that oil oxidation is losing. You're losing electrons, and then the opposite for reduction, right? You're gaining electrons. It's a pretty useful mnemonic that you want to remember. So, you guys got any questions so far? Are we good? Okay. Let me. Okay. Um. So, can someone tell me what kind of reaction this is?
Synthesis.
Synthesis, yeah, because A plus B yields. Yeah, you guys got this. I trust you. Um, okay, so now we're gonna go on to okay. So can someone tell me what the law of conservation of mass is?
It's like
Mass has to be conserved.
Uh,
Mass
could
can
could you
be
could you please elaborate on that statement?
Mass
yeah.
cannot be destroyed or created.
Okay, yeah, it can only change. Well, good. So let's just say um okay, this is not what I want. Hold on. Okay, whatever we'll go with that Haber Wash. All right. You guys know? Do you guys know how to balance equations? I don't know if I like have to teach you guys this.
you add the coefficients.
We did it at one of the sessions.
All right, cool. Yeah, I'm still gonna explain it for the purposes of the video. You know what I mean? So this is a review guide for you guys. It's fine. Just make sure that you know what's going on. So so an N2 plus H2 yields NH3, right? There's how many N2s on the left side? I'm sorry, how many nitrogen atoms on the left side?
Two,
How many hydrogens?
two.
Right, and there's obviously one nitrogen and three hydrogens on the right side. And that violates the law of conservation of mass, right? So can someone tell me why we can't just change this to N why can't we just change the right side to N2H2?
That's not the same.
Then it becomes a different thing.
Yeah, it's a different compound. So what we can do is make it so that we have a different amount of that thing, right? I'm actually gonna click on this video because I trust that it explains it well. Okay. So that's what we did. We just counted up the amount of atoms on each side. Okay. So here's the first step, right? First you want to make sure that there's enough of a thing, right? N2, we have two nitrogens on the left side, one on the right. So we can just put a coefficient of 2 in front of the ammonia, NH3. So now we have two nitrogens and six hydrogens. And then, now we have two nitrogens, but only two hydrogens on this side. So we can go ahead and put a coefficient of 3 on the hydrogen if he actually writes it. He does not write it. Okay. But yeah, you can just put a coefficient of 3 in front of the hydrogen to make sure that you have an equal amount of elements and the same kind of elements on both sides. Okay. Let me see. Hold up. All right. So I'm gonna give you guys some time. Try to balance this. Sodium hydroxide plus sulfuric acid yields sodium sulfate and water. Yeah. When you guys are done, just yell out whatever you have. If you're having trouble, I'm just gonna play the video. So yeah.
Is it 4 NaOH, 2 H2SO4, 2 Na2SO4, and 4 H2O?
Could you say that again?
Is it are the coefficients 2, 4, 2, 4? Oh,
Two,
Hmm.
um,
It's 2-1-2-1, right?
2,
Oh
1,
wait, right.
2.
1-2-1.
Yeah, okay. Yeah, you guys know how to do this. But something interesting that this guy says is that you see here with sulfuric acid and then sodium sulfate, right? You still have that SO4 ion. So you can basically if there's equal amounts of them on both sides, you know what I mean? You can just straight up group them in a one big SO4 ion, instead of listing the S and then adding the O4. It can sometimes be quicker to just group them into these big chunks. Um, so yeah, if you see any patterns on both of the side, feel free to take advantage of that. It can definitely save you like on a bonus or something with like a long equation. But yeah, looks like you guys got this. Let me see. What do I gotta teach you guys next? I said, okay. I want to teach you guys about equilibrium because I feel like it. Um, so can someone tell me what chemical equilibrium is?
Is that like when the charges are the same on both sides?
Not
It's
quite.
when
Anyone have
uh
any other
is it
ideas?
when like the forward and
Oh, it's
backward
like going forward.
reaction rates are the same?
Yeah, you got it. So take this for example, right? H2 plus I2 yields 2HI. Um, so this is like your traditional chemical reaction, right? H2 plus I2 yields 2HI. But what's interesting is that here with reversible reactions, that's what we call them, you can just straight up flip it and a 2HI yields H2 plus I2. And you'll see this pretty commonly with like weak bases and stuff, weak acids. We'll go over that later. Um, so yeah. Equilibrium is when this forward and backwards reaction reaches the same rate. So don't be confused and think that there's no reaction happening. Just think of it as like equilibrium within like a cell or something. You have equal stuff crossing the cell membrane generally at the same time. That basically carries over to chemistry as well, right? That equilibrium state where the forward and backwards reactions are the same. So okay. And with equilibrium reactions, there is a way to predict which way they will go. Don't yeah, that's fine. So yeah, there's something called K, the equilibrium constant. And it basically tells us which direction that this equation is going to go. Direction as in if it's going to go right, it's going to favor H2O, it's going to produce more H2O. If it goes left, it's going to favor the reactants. And it's basically the E yeah. So what you get here is, for example, right, H2 plus O2 yields 2H2O. You have the equation C big that's pretty funky to read. You guys can read. So what you have here is that the reactants are on top. This probably explains better. The reactants go on top, and then what am I saying? The products go on the top, and then the reactants go on the bottom. My God. And here you have H2O in brackets. That just indicates, the number of moles. Right. Okay. Yeah, so that's the big letters, that's the concentration, right? So here you have the concentration of H2O squared because it has a coefficient of 2. Remember this equation? You raise the power of the concentration of your molecule or whatever to its coefficient. And then you would divide that by the same thing for the reactants, right? Concentration of hydrogen squared times oxygen. The 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 concentration of oxygen. And there you get K, the equilibrium constant. So if K is large, that is if K is greater than 1, it's going to favor the products, right? And if it's less than 1, if it's small, then it's going to favor the reactants. Because, obviously if there's more of the product, it's going to want to reduce more of the reactants, if that makes sense. You guys have any questions? It's kind of confusing. We're good?
So it favors the
Okay.
products if it's less than 1, right?
What?
It favors the products if it's less than 1, right?
If it's less than 1, it favors the reactants. Okay. So yeah, it's just calculating equilibrium constant. So can some of you guys tell me, right, if equilibrium constant is, concentration to the coefficient, can someone tell me how you can maximize this, maximize K?
Having the most moles and big coefficient, like having the most of the products, a lot products.
Yeah. Yeah, tons of products and then little reactants. It's gonna increase the K. Um, so let me show this. Yeah. So there's something called a Le Chatelier's principle. It's it sounds pretty confusing, but it's actually pretty intuitive. So think about it. If you have this equation here, right? H2 plus 3H2 plus N2 yields 2 NH3. If you were to increase the NH3 concentration, what would happen to the equilibrium constant?
It will go up.
It would start favoring the uh products.
Um, Shoot, I'm bugging. Okay. Let's see. Equilibrium constant K. Connie Kennedy probably explains it better than I can. Yeah. So equilibrium constant, yeah, I explained it pretty badly. It doesn't mean if it's favoring something, it just means that the equation itself, you know what I mean? So if it's at equilibrium and you find an equilibrium constant and it's high, that means that the equation is favoring the products. All right. And then the reaction quotient is used to find, yeah, the reaction quotient is used to find if a reaction is at equilibrium and um which direction it's gonna go. That's yeah. Um, you guys know this? Yeah. So the equilibrium constant just tells you what's going to happen at equilibrium. And then reaction quotient is basically the same kind of calculation, right? Concentration to the coefficient over, you guys know. And then if your reaction quotient is different from your equilibrium constant, then that means that the equation is not in the equilibrium and it's going to, change. So if Q is greater than the equilibrium constant, then it will try to make more reactants to balance it out and reach that equilibrium constant. So what you want to know that is at every reaction, every reaction wants to be at equilibrium. If it isn't at equilibrium, it's going to try to get to equilibrium. And right, if Q is less than C, then the concentration is going to go forwards and produce more products. You guys got that?
Which side does it favor when the constant's less than 0? Wait, like less than
If
1?
it's less than 0 or it's less than 1, then that means that the left side of the reaction is favored, the reactants. Because if you have a very little amount of your products and a lot of your reactants, that just means that your reaction favors having reactants. So we can apply this with Le Chatelier's principle. It sounds kind of complicated, but it's pretty intuitive. So let's say you have this equation, right? 3H2 plus N2 yields 2NH3, and it's at equilibrium right now. If you increase the amount of H2, right, would it still be in equilibrium?
So
No. So the reaction, right, it's obviously going to try to go to equilibrium. So what you've done by increasing the hydrogen, right, you have now increased Q because it's reactant. And see here, if Q is greater than K, then it's gonna. That's weird. Okay. Since you've now sorry, what am I saying, bro? You decrease your reaction quotient, right? And since Q is now less than your equilibrium constant, it's going to go in a forward direction, my bad. And so it's going to keep progressing forwards until you have enough ammonia to make the equation at equilibrium again. And it's basically the more formal definition is that disturbing a system at dynamic equilibrium shifts the equilibrium in a direction that counteracts the change. So if you have more reactant concentration, then it's going to want to form more products and vice versa. And this also functions with exothermic and endothermic reactions. So what happens in exothermic reactions? Is heat released or is it absorbed?
Released.
Released.
Released, yeah. So you can basically imagine heat as a product, right, in exothermic reactions. So if you were to increase the temperature, then that would shift the reaction further to the reactants because heat is essentially a product, right? It is a product in an exothermic reaction. And then same with pressure, right? So let's just say I can't find any good examples. Sorry. So let's assume, right, you have six you have like a lot of molecules in a really, really tight container, right? Is the pressure going to be high or low?
High.
High, yeah.
High.
So obviously, right, the equation doesn't like that. It wants to be under the least stress as possible, you know what I mean? So if you have gaseous hydrogen and gaseous oxygen forming liquid water, then it's going to prefer that liquid water, right? Because it is the least amount of gas molecules, so it's gonna be under the least stress. So yeah. Guys got any questions? This is kind of complicated. Okay. Yeah, one more thing, and then I think we should be good. I love Khan Academy. Direction push. Okay, I can't find it. Okay. So this is basically just a visualization of what happens um, in the equilibrium reaction, right? So you see additional oxygen, right? It's at equilibrium. Your K is at whatever K is, and you're adding additional oxygen to decrease your Q, your your reaction quotient. So does anyone remember what's that going to do to the equation if your reaction quotient is less than your equilibrium constant?
And
Oh,
then
it's
come
true.
forward, right?
Yeah, it's going to go more forwards. So I'll have you guys just answer this question. Which of these graphs shows rate of the forward and reverse reactions, right? So all of them start at, a base value that's all the same because it's at equilibrium. And then that equilibrium's disrupted by the injection of oxygen. So which one of these graphs? Oh yeah. And then the forward's the solid line, reverse the dashed line. I should probably zoom out. Okay. So which one of you guys, which one of these graphs do you think represents this reaction the best?
C,
C? Why do you think C?
because it starts with a lot of forward reaction and then it slows down to kind of like match up.
Okay. Yeah, you've got the right idea with the spike of the forward reaction, but
Is it A?
it is A, yeah. So the difference between A and C, instead of the forward going down, this means that as the forward reaction increases, I should zoom back in. So if the forward reaction is spiking right now, you're going to have a lot of SO3. What does that mean? Then it's going to want to go back, and it's like a back and forth, until you can reach a new equilibrium that can be established. All right. Guys, have any questions? If not, I think we can just end this meeting here. Yep. All right. See you guys next time.
Thank you.